Okay, see. Okay, good morning, everyone. Thanks for being around. Today we are starting this probability session about the 60th anniversary of Simvestab. Simvestab started 60 years ago, and one of the three departments that started with the institute was precisely mathematics. So the Department of Mathematics has already 60 years old. So happy birthday to our department. And for this session, we have the pleasure to introduce Professor Rodrigo Bañuelos. He's from Purdue University in the USA. He's very well known for all his work about harmonic analysis in probability, among other things. He did his PhD in the University of California under the supervision of Professor Rick Durrett. He has one book, very nice book, called Probabilistic Behavior of Harmonic Functions. So one of his, he has several citations, around 12 students, PhD students. Just to give you a brief idea, he's been elected fellow of the American Mathematical Institute Society, sorry, and also he's got something called the Martin Luther King Jr. Dreamer Award. So as I told you, he's an expert on harmonic analysis in probability. And for starting this session, we have the pleasure to have Professor Rodrigo. So go on, please, Professor, you can start your talk. Thank you.
Thank you very much. So before I start, let me thank the organizing committee for the invitation and all of you for the hospitality. So this talk is generally speaking a bit of a survey talk on the uses of probability, more precisely Martingale theory, to study Calderon-Zygmunt operators. And I would like to illustrate maybe this application with one particular problem, but it will be not so technical, I hope. We will have formulas and so on, but probably is not the place to get engaged in very deep technical things and prove everything that we have. So let me start by reminding you what is a Calderon-Zygmunt operator. So a Calderon-Zygmunt operator is an operator which is defined in a collection of smooth functions, which is bounded on L2, okay, and it has the form that it is an integral against a kernel, right? And this is a principal value. So this kernel typically has degeneracies or become singular, which is the reason why they're called singular integrals on the diagonal when x is equal to y. And the operator is called a Calderon-Zygmunt kernel, okay? If it has some of these decay conditions, so on the diagonal, it decays like x minus y to the n, or has a singularity, blows up like one or like x minus y to the 1 or x minus y to the n. The gradient, if you take the gradient in x or the gradient in y, has a similar decay, a similar blow up on the diagonal. So such t's, the point of such t's is that they are bounded from LP to LP. When p equals 1, they fail to be bounded. There is an inequality which is called the weak type inequality, which I will not discuss here because the probabilistic tools are quite powerful to study LP inequalities where p ranges between 1 and infinity. And although they work extremely well in probability for all ranges of p, when you try to transfer the inequalities to the singular integrals, they do not work. So the point here that I want to emphasize is that with this theory, with the Calderon-Zygmunt theory, the behavior of the constant of p goes to infinity blows up linearly in p, as p goes to 1, it blows up as 1 over p minus 1, okay? And this, in fact, is the best possible behavior of this constant asymptotically. The constant APN, if you fix a p and now look at it as a function of n, this is exponential as n goes to infinity. Now, this exponential as n goes to infinity is really not very good if you want to do these results as n goes to infinity. And this is where the probability comes in. So let me remind you, if you have not seen these, of the two classical examples, which are actually convolution types. So this is the kernel k is just a function of one variable. And then you integrate x minus y, kx minus y. So this one is 1 over x minus y, 1 over pi. So this is the classical Hilbert transform. The Fourier transform of the Hilbert transform is just I signed of f, the Fourier transform of f. Now, the Riesz transforms, which are the higher analogs of these, are very popular and can be defined in many different settings. And these are these singular integrals, which Fourier transform, which is, if you look just in one dimension, it becomes again just the Hilbert transform. But in higher dimensions, you have these multipliers, which are also they are clearly bounded in L2 because of Plancherel's theorem. But in addition to that, they have a connection to semigroup theory. So this is the derivative in J of the Laplacian to the minus 1/2 of f. Okay, so these can be defined in terms of Fourier transform or in terms of semigroups. So now, what is the motivation for this? The motivation to study this came from a paper of E.M. Stein in 1983, which starts out with really what the purpose of this of his paper was, and also in some sense of this talk. So the purpose of this note, he says, is to bring to light some further results whose trust is that the certain fundamental estimates in harmonic analysis in Rn have formulations with bounds independent of n as n goes to infinity. And then he gives various examples. So the classical Hardy-Littlewood maximal function. So he proves that the LP norms are independent of n as n goes to infinity. The spherical maximal function. And for the interest of this talk is he proved various multipliers also have constants independent of dimension and in LP, and most notably the Riesz transform. So AP, here's his theorem, that AP, the Riesz transforms, vector of Riesz transforms has a constant in LP, which is independent of P, right? Now, well, here is something that it happened in Stein's proof. So he used the theory of Littlewood-Paley to give his proof, you see. And he obtained that if you fix an n, then the constant that he obtained, okay, so is independent of n, but it grows as p of order 1 over p minus 1 squared as p goes to 1, and also of order p squared as p goes to infinity. So in other words, he corrected the dependence on n, but ruined the dependence on p. Now, these inequalities, of course, were also extended afterwards to the Ornstein-Uhlenbeck setting for Riesz transform, the Ornstein-Uhlenbeck setting. So, in fact, my thesis, PhD thesis in 1984, was to not only get the independence of n, but correct the dependence in p. In other words, get the actual big O of p as p goes to infinity, and 1 over p minus 1 as p goes to 1. And of course, the fact that this blows up at 1 and it blows up at infinity reflect the fact that these inequalities are not valid at p equals infinity and p equals 1. So they're substitutes for that. Now, well, here's what Stein says at the conclusion of the theorem of his paper. He says, the above results raise the following general questions. Can one find an appropriate infinite dimensional formulation of that part of harmonic analysis in Rn, which displays in a natural way the above uniformity in n? A related question is to study the limit as n goes to infinity of the above results, insofar as such limits have a meaning. One might guess, and here's the punch, that further understanding of these questions would involve, among other things, notions of probability theory, Brownian motion, and possibly some variants of the central limit theorem. And the fact is that Stein was absolutely correct in that. Many singular integrals, you cannot show not only that they are independent, the independent bounds in terms of the dimension, but in fact, you can sometimes even compute the norm of these operators. Okay, the LP norm, which is really much more than just getting bounds. And examples of these have been the Riesz transforms. In fact, that was part of my thesis. Various types of Fourier multipliers and versions in very wide geometric settings, okay, like manifolds and vector bundles and all sorts of settings. He was also right and quite correct in his statement that the central limit theorem plays a role also in obtaining analogs and infinite that do not depend on dimension. And this is something that I did sometime in the 80s with a proof of something which was called the Gandhi-Stein conjecture on the behavior of harmonic functions. The book that was mentioned earlier actually deals with a lot of this work. So I'm not going to talk about these. So we're going to talk just about the first point there about LP estimates. So again, the talk is the literature. This talk is about topic one. The literature, let me just say here, is on probabilistic techniques for estimates for norms of Calderon-Zygmunt operators. Is really huge now. So it has been applied in many different settings. And what I like to do is give you a bit of a survey and illustrate with a very simple to state problem that has been of interest for quite a long time on the norm of the discrete Hilbert transform. So let me give you a little bit of pre-Calderon-Zygmunt history. So if you take two polynomials, so f, okay, so or infinite polynomials, doesn't matter because the constants here that we will obtain do not depend on n, the capital N there. So you can just take an infinite series, a Fourier series. So the question of considerable interest, so f tilde is called the conjugate. So you interchange the sign with the cosine and that's about and a minus with a plus, and this is called the conjugate functions for a reason that I'll tell you in a minute. But the question of considerable interest in the early 20th century is how does the size of f, control the size of f tilde? And by size, we mean in terms of LP norms, right? So if in other words, if one is an LP, is the other one also an LP, right? With comparable norms up to constants that depend on P. So the LP boundedness of the Hilbert transform, so this is the non-periodic, so this is called the periodic Hilbert transform, and this has an integral formula too. But the Hilbert transform, right, is as we stated already, this question. Now the Hilbert transform, because the Fourier transform, the bound that you have in terms of the multiplier is equal to 1, you immediately have a Plancher's theorem that this is an isometry in L2. So it takes L2 to L2 and the norms are equal. Again, it's a singular integral, so it doesn't take L1 to L1 and it doesn't take L infinity to L infinity. But here's a very famous theorem of Marcel Riesz, published in 1927, proved in 1923. So if you ever worry about your papers getting a long time to publish, you can think of Riesz and this famous paper. And I'll tell you a little bit of the story of these. Now, there's also Kolmogorov inequality that was proven in 1926. That even though the inequality fails for p equals 1, the L1 inequality, there is a substitute, and this is a substitute that works for all singular integrals, Calderon-Zygmunt singular integrals, okay? So now, let me tell you a little bit more about this history around this in the 1920s for this problem. So, in the same paper where Riesz proved the inequality for the continuous Hilbert transform, and I will call that the continuous Hilbert transform, he proved that if you take the analog, right, so of course you cannot do principal value here, you have to remove M completely, M equals 0 completely. He proved that the discrete Hilbert transform, as a consequence of the continuous version, right, by approximations, Riemann sums and so on, that the discrete Hilbert transform is also bounded in P, okay, and not furthermore, that it satisfies the norm, okay, whatever the norm of the discrete is less than a constant times the norm of the continuous one, and on the other side, the norm of the continuous one is always less than the norm with constant equal to 1 of the discrete one. Now, Tishmarsh in 1926, also published in 1926, proved in 1924, so he was a little bit faster than Ries, proved that the discrete Hilbert transform, starting from the discrete Hilbert transform, he proved the discrete Hilbert transform is bounded in LP, and that the two norms are actually equal. That is, the best constant in the little LP and capital LP inequalities for the discrete and the continuous Hilbert transforms are the same. Now, unfortunately, the following year, right after his paper was published, he had to make a correction. And here's a correction. So his inequality that the discrete is less than the continuous was incorrect, is incorrect. So he says, in paragraph 4 of my paper on reciprocal formulas involving series and integrals, the proof of this inequality is incorrect and should be deleted. This does not affect anything else in the paper. Now he goes on to reveal that in fact he said the following references of this work of the work of M. Ries should have been given. I should also have said, so this is the paper that proves a continuous version, because in fact Tishmarsh followed the proof for the discrete one setting, follow Ries's proof, and he also says I should have said, well, he should definitely have said it, that I was already familiar with Ries' method and not merely his results when I wrote my paper. Now, Tishmarsh was a student of Hardy at that time, and there seemed to have been a good competition between these four people, right? So there's Hardy, there's Littlewood, Ries, and Tishmarsh. And here's an interesting article that I really liked after somebody pointed it out to me on the history, a little bit of the history of this competition. So this is a paper by Mary Lucy Cartwright, who was Hardy's last student, in the Bulletin of the London Math Society in 1982, where she publishes various letters that were interchanged between Hardy, the group in London, and Marcel Ries in Stockholm. So here's, let me read a little bit because I think it's quite interesting. So they were exchanging early on in 1923, they were exchanging letters between Marcel Ries and Hardy and various the other three in the other two in London about various things, but they communicated really always through Hardy. Well, here is a correspondent at the end of Ries's letter, June 19, 1923, he wrote, so this is Ries, this is in French and you can read it just as easily as I am. I am not a French speaker in any way, but here's what Marcel Ries says. He says, I have proved, okay, the two trigonometric series, conjugate trigonometric series, are the same series in LP, right? The same Fourier series of class LP. In other words, if one is an LP, the other one is also an LP. All right, and he left it at that, and then they continued to exchange letters, and then on the 18th of December 1923, Hardy wrote to Marcel Ries. Some months ago, you said, I have demonstrated the boundedness of the Hilbert transform, essentially what that is, and he says, I want the proof. Very authoritative, right? Both I and my pupil Tishmarsh have tried in vain to prove it. Some attempts go close, and I feel that probably I could do it with sufficient determination, but it is not worthwhile if you have done it already. As team is engaged on corresponding questions about integrals, it is of vital importance for him to have the proof of this rather fundamental theorem. So please send me the grand ligne de la dame, right? The most important lines of the proof, so that need be, we can reconstruct it without serious difficulty, or B, a complete proof. I need hardly say that I should be delighted to get it published here. All right, so this was a letter sent on 18th of December, 1923. Now look at this, 23rd of December, 1923. So this is almost as fast as email, I would say, from Stockholm, right? So the letter went from London to Stockholm, and here's Marcel Ruiz's response. Here are the grand ligne de la dame, right? Here's the important lines of the desired proof. And he goes on to explain how he proved the theorem, right? So he writes down, that analytic function, which has boundary values f plus if tilde, and then he formulates what he needs to prove. And then he goes on to say, look, the only thing that I need to do is use Cauchy's theorem. However, Cauchy's theorem for p even integers, all right? So if you take an analytic function, raise it to an even power, right? So you get back an analytic function, you can apply Cauchy's theorem, and then you can play around with Hilbert's inequality, which is what he did, and voila, there comes the proof of the theorem. All right, so at the very end of these letters, right, the letter from Marcel Ruiz to Hardy, he explains how he discovered the proof for the even integers. Now, if you have even the proof for even integers, you already also have it for all p's because of something which is called Martingale's interpolation theorem, which was already available at that time. So once you prove it for two p's, you can get it for all of them in between. And so you prove it for p equals 2, and then you prove it for p equals 4, and you get it for all p's between 2 and 4. And the same thing with every, as you go on. Okay, so he says for p equals 2, he says the most important step is to forget about Parsifal's theorem, okay? And he said my proof of this inequality has a curious history. He says that he was preparing an exam for a student who, according to my translation of French, was not terribly bright. Okay, no, so not a very generous comment, but he says the examination contained 8 problems, of which it included the usual case p equals 2, and then he said, I then started thinking, I realized that my student did not know, the student did not know Parsifal's identity or the boundedness Planchar's theorem. So he said, I was wondering how will he proceed with the proof if he did not have that. And then he discovered that, in fact, he could apply Cauchy's theorem instead of Plancharel for p equals 2. And then he said, then from there, he went on to p equals 4, and then he got the proof. Now, Hardy wrote back immediately, look at this, 5-1, right? So again, this is 24, right? So 5th of January 24th. Many thanks, you supply all that is essential. I have sent it to your letter to Tishmarsh. Most beautiful, most elegant and beautiful. Of course, p equals 2 is page 2 is the real point. It is amazing that none of us should have seen it before, even for p equals 4. Your student's life is not entirely without value, though I suppose he will never understand why. Well, not terribly nice, right? But it is history, and it's kind of interesting how this works. So you see, Tishmarsh definitely already has in 1923 Ries's paper, and then he followed Ries's paper for the discrete version, so he had to make that correction for sure. But any case, so Picorides in 1972. So the problem of finding a proving that these two norms are the same for the discrete and the continuous has been around since that time. And in fact, some people attribute the conjecture earlier on to Hilbert, but I have never seen it in writing, so I'm not going to go that far myself, but certainly the problem has been around. In 1972, Picorides, who was the last student of Anthony Zygmunt, published the proof that that the norm of the Hilbert transform, right? P star is this Burkholder constant, which is the maximum of P and Q, right? The norm of the Hilbert transform is a cotangent of pi over 2 P star. So it's really P as P goes to infinity. In other words, you have to put in Q. So this maximum of this is P and Q, where the P and Q are conjugate exponents. Right, so here's a more explicit expression, right? So he proved that this inequality holds, and then he proved by finding extremals. Right now, there are no extremals. So this inequality doesn't have extremals, but what he has is that asymptotically you cannot get better than this constant in the inequality, right? So our theorem, my theorem with Mateusz Kwaśniewski from Wrocław University, as we were talking earlier, says that in fact this Hilbert transform, the discrete Hilbert transform, also has an upper bound, which is the cotangent of pi over 2 P star. You see, and in particular, then, since this is the L infinite, this is the norm of the continuous Hilbert transform, we have the corrected Tishmar's inequality, namely that you can do this with constant 1, right? So together with Ries, which we already knew, the other inequality, you have that in fact the norm of these two operators are the same. Of course, one thing that one should notice here is that they were working at that time, well, not everybody who has been working on this problem has been approaching it that way, but without knowing the norm of the Hilbert transform, right? The continuous version. Here we knew that this was a continuous version, so the only thing we had to do, quote unquote, only thing, was to prove this bound, and then of course immediately we will have then that this is less than or equal to the continuous, the discrete is less than or equal to the continuous version, right? So I want to tell you a little bit of how this inequality comes about. Before I do that, let me mention, so there's enormous amount of work in terms of trying to extend the proofs of the Hilbert transform to the discrete, the continuous to the discrete. In fact, Gockenberg and Kuprindik in 1968 proved that the Hilbert transform before Picorides, a few years before Picorides, that the Hilbert transform has this bound, the desired norm, when P is an even integer. And they did it by a clever identity, namely, I'm not going to really go through it, but that if you take the Hilbert transform, square it, you get twice the Hilbert transform of F times the Hilbert transform of F plus F squared. This inequality, this identity you can prove just by computation, but it is a clever identity. Now, after you make the observation that the 2P norm square is equal to the P norm of the square, Minkowski's inequality, Holder's inequality, essentially gets you this inequality. And then you see by induction, then you already know the inequality for HP, you want it for H2P, and then you use this simple trigonometric identity and you get the inequality. The inequality that the P norm of H is less than or equal to the cotangent pi over 2P, all right, for this P. So this was again before Picorides. And then this argument actually was extended again for even integers, right? By Brzezinski in 1984, and then also by Lang in 2007. And there are lots and lots of proofs of this inequality from harmonic analysts and complex analysts and so on, if you don't care about the constant CP. Right? So this is there's quite a lot of this, right? But not with the best constant. So the theorem that we proved for general P was already proved for P even integers using these kind of tricks of identities and so on, right? So now Our proof rests on inequalities for stochastic integrals. These inequalities are not new. The inequality of Dan Burholder, but the version that we want here is this inequality that Gang Wang, who was my postdoc here, and I proved in 1995. So this is kind of an old theorem. But here's the point, that if you take two stochastic integrals, one in n-dimensional Brownian motion, right, one represented by k, right, dot dbs, the other one by h dot dbs, and you suppose that k of s in the norm of these, right, so it's a vector in Rn, is less than or equal to h of s almost surely. This is called subordination, and you also assume for the other k's that they are orthogonal. Then if you have subordination, Burholder proved in 1984 that you get something which is called, again, this constant p star minus 1, which we already mentioned before, times the norm of the m. And this holds for any time t, fixed time, continuous time, right? Or stopping time. This is true. This is true for any t. And then the same thing holds if, in addition to the subordination, you assume orthogonality, but then you improve the constant, right? So this is what we proved, and this is the inequality that we will use for this proof. Now, let me go through, okay, and give you a proof of Picorides theorem, because the proof of Picorides theorem that I will give you is sort of like in the style of Marcel Rees. So in order to prove the inequality for the discrete, what we need to do is forget about all the proofs, they have failed, right? And then try to find a proof for simple case, which may have a chance. Now, this proof, is okay. So it's probably been around for a very long time, but you can do it with a very general construction. Now, again, the proof of Picorides theorem with the best constant is an exercise in many books. So it's a very simple. Now it's got a very simple proofs. But here's one proof using probability. So let's take the Poisson kernel, right, in the upper half space of the real line. Right, and then you take the harmonic extension of these by integrating of the function f, by integrating it against the Poisson kernel. So this function, as a function of x and y, is harmonic in the upper half space, and you see as y goes to 0, the boundary value, right? So this harmonic extension gives you the function f. As y goes to infinity, if you this of course goes to 0 because you're multiplying here by something. This is square and this is linear, so as y goes to infinity, it goes to 0. But if you multiply by y times pi, both sides of this inequality, you see your y becomes y squared here. 1 over pi goes away, and then you have y squared over y squared. So this becomes the integral, right? So y times pi use of f of x comma y is just the integral of the function f for any x whatsoever, right? So in particular, right, when x is equal to 0, you always get, as y goes to infinity, that this is equal to the integral of f. Now that is very nice because we also have a representation of the harmonic extension in terms of Brownian motion. And the Brownian motion is just the Brownian motion in the upper half space. We started here at 0, y0, and we look for the time that the Brownian motion leaves the upper half space. And then we go and you see, just because of the solution of the Dirichlet problem in terms of the expectation of the function at the exit position of the Brownian motion, we have a representation for u. So here's what we have, if we want to think probabilistically from the previous discussion, is the pi y times expectation gives you the integral of the function. Now, if we apply Ito's formula, so we can use this in a minute. So if we apply Ito's formula, so here's Ito's formula applied to u, we see because u has boundary values f, we have a representation of the function f along the exit position of the Brownian motion from the upper half space as a stochastic integral. Now, let's do a transformation of this. In other words, construct another random variable, which we can call m, right? So this is your n here. So let's take this matrix A, put it here, right? And then notice that, of course, this matrix has norm equal 1. So the norm of Laplacian of u of f, of the gradient of u of f, by the Cauchy-Riemann equations is exactly the norm of the conjugate function, the function which makes u plus iv analytic, right? And the gradient of v is just this transformation. So these are very nice ways to write the Cauchy-Riemann equations. You just take the gradient of the function f, you apply this function which is with this matrix which is orthogonal to it, and you get back out the Cauchy-Riemann equations. So here's the conjugate. So since we apply, you can also apply Ito's formula to the conjugate harmonic function. This is nothing more than the gradient of the conjugate harmonic function. So this is nothing more than Ito's formula. You see, but now if you let t go to tau, right? So just look at these on the exit position of the Brownian motion. You get a representation for the Hilbert transform of the function f, right? The conjugate harmonic function, which is equal to the stochastic integral. Now, the stochastic integral is subordinate to the v, because the norm of the matrix A is less than or equal to 1, is subordinate to the stochastic integral represented the function u. And because h is orthogonal, the u and the v are orthogonal. So here is the inequality that we can get from the Martingale inequality, or the stochastic integral inequality with the orthogonal Martingale and subordination. This inequality, right? Now, it turns out, okay, that again, you multiply by pi y and let y go to infinity. This quantity disappears. These quantities appear also, these u sub f of 0 y. And what you get is just the expectation, right? Y pi y times as y goes to infinity, you get the expectation of h of f, right? And this is nothing more than the integral of h of f, and you're raising it to the pth power, right? And on the right-hand side, you get the function f. So in other words, here's the conclusion of this little exercise, that if you define this operator, okay, so let me do it a little bit more. So the similar construction here. So oops, I got off here. Okay, so for general 2x2 matrix, you can do the same construction, right? Except you have to take the conditional expectation. You do not come back to a function, just a function of the terminal position, but you can take the conditional expectation. And then here's this theorem, right? That says that exactly the same as we did before, by taking by using the fact that conditional expectation is a contraction in LP. So you just go out to immediately to the stochastic integral. Then you apply Berholder's theorem here, and you have exactly this inequality, right, with p star minus 1 for any matrix A. And the matrix A can even have variable coefficients. If the matrix A is orthogonal, then you apply the other theorem with orthogonality assumption in addition, and then you get the cotangent, right? So now this isn't just Martingale's, right? So now you take y, pi y times pi y and let y go to infinity, and then these integrals become just integrals over r. Okay, so this construction leads to a collection of Martingales even in Rn, a single of operators in Rn. And the kernels are very, very precise, right? It's very precisely stated, in terms of Poisson kernels. So this is a kernel. And of course, the question is, and they have bounds, and the bounds are beautiful, right? Except they depend, of course, on the norm of the matrix A, right? But if you take matrix A, for example, like the Hilbert transform, you get exactly the inequalities for Picoides, right? And in general, what other things do you get? You get a lot of Calderon-Zygmunt singular integrals with this construction, and of course the Calderon-Zygmunt theory doesn't give you LP bounds for these. It gives you LP bounds, but not LP bounds independent of dimension, as it is the case here. And now So some of these, some are convolution operators, but some are not. Okay, so this is a very precise collection of Calderon-Zygmunt singular integrals, and the fact that they are Calderon-Zygmunt you have to prove because you have to take these kernels and show that they satisfy the blow-up singularities that are required. They contain Riesz transforms in Rn, Lie groups, manifolds, Ornstein-Uhlenbeck, many. You can replace Brownian motion, as you may imagine, by various other processes, including Levy processes. In fact, I wrote a paper with Krzysztof Bogdan, also from Brussels University of Technology, on these constructions. And there is a paper that just appeared in Journal of Functional Analysis, which is joined with various other authors, in which we explore these for these constructions and construct the singular integrals for Schrodinger operators. So this goes very far in terms of constructions. But now you see, what did we learn here? About the proof here that I just presented for Piccoli's theorem, that you can extend it in many directions. But now, what we want for the discrete Hilbert transform is a Brownian motion in Rn that only exists at the integers, right? And so we want to replace the Brownian motion, conditioned to exit the domain, right, by a Dubh process, okay? And this Dubh process should run in the upper Hess space, but when he gets to the boundary, he can only exit through the integers, right? It doesn't go exiting like the Brownian motion at any other point. And then we hope that with this construction, we will be able to get new collections of singular integrals which are discrete and which will give us, when we do the analysis, the discrete Hilbert transform. So we'll repeat these for the discrete Hilbert transform. So again, you take these Poisson kernel, but you take the pole only at the integers, right? And then you construct this function h of x comma y, which is in fact called the periodic Poisson kernel, right? And it is equal to some expression that one can write. And lo and behold, something beautiful happens because we are in R, and you can write down this periodic Hilbert transform very precisely. Okay, now H, of course, is positive harmonic, right? You can differentiate the Poisson kernel is harmonic, so you can bring the Laplacian inside the sum after doing some calculations, and you can show that this function is harmonic. It's positive harmonic, right? So you can do conditioning with this function. Now, for every function f, so now I'm going to use function f as a sequence, right? This is a function from the integers, right? Into the real line, and just the value at n is equal to an. And we can suppose that they have compact support, right? Everything here is a priori. So we can assume that all functions are as nice as we want. And compact support sequences, it just means that it's a finite sequence, right? A finite sequence. And then you construct this function, right? This u sub f, right? Okay. This function is exactly the analog of the harmonic extension of the harmonic functions. Now, u sub f now is harmonic in R2 plus, but it's harmonic relative to this operator, which is the Dubh transformation of the Laplacian by this harmonic function h, right? And what happens? What happens is that this function, when you look at the boundary values at the integers, right, is equal to the sequence, right? So this is like a harmonic extension of the sequence to the upper Hess space using this Dubh process, right? Okay. Now, if you then want to do the analysis that we just did, you take the Dubh process, which is Brownian motion with a drift, right? And you again apply the Ito's formula. So this is exactly the same Ito calculus, except for the Dubh process. And you get a representation of Martingale, right, which is equal to the gradient of u sub f evaluated as z, this Brownian motion dot dbs, right? So these, right? So these is not the same, is not, this is running in the filtration, of course, of Brownian motion, but extended to this this Doob H process Z sub t, but it's got the same structure as the theorem that we stated for the LP bounds. And then you take a 2x2 matrix and you construct the transformation of it, NT. All right. Now the problem is that this is no longer these. If you undo Ito's formula, this is no longer a function like these right here, which is a function of the exit position. So, but certainly this martingale is dominated subordinate to the martingale M, right? And if A is orthogonal, then we have the following theorem, right? So we need to condition this back to exit at 2 pi n, right? Because otherwise we will not have a function back on the real line. But here's what you get when you apply the Martingale inequality. So here's what you get when you apply Burkholder's inequality. And if you have orthogonal, then here's what you get when you apply the inequality with Gang-Wang that I mentioned earlier. And here's what happens. Okay, so you do the same construction as y goes to infinity. These operators, right, actually converge to a class of operators, which are called script T A of F, right? And they have these little LP norms. So here you have to do some work, right? So you have to show that these doing this condition in Brownian motion do condition, and you get not Lebesgue measure, but you get the discrete measure on the ladders, right? So that the expectations become little LP expectations. So here's for any A, and here's for any orthogonal A. Now, let me see. I'm going to try to finish quite soon here, but the construction, you can do the construction that we just did exactly the same, and you get, you see, these discrete operators. And the discrete operators, the kernel is equal to this quantity here. One can compute that, and believe me, it takes a bit of computation. But these integrals have the bound p star minus 1 for any A, and it has a cotangent pi over 2p star for any A that is orthogonal. So the construction, of course, can be done on RD, but D bigger than 1, okay? But much more work needs to be done if we want to do it in RD. And this is actually subsequent work with one of my former students, Kim, who is a postdoc at the University of Illinois. He's actually a new postdoc there. Now, the question is, are any of these things include the discrete Hilbert transform? And here is something that is somewhat disappointing. So if you take the obvious transformation, which is the one that gives you the continuous Hilbert transform when you do the construction, you get a kernel, but the kernel actually is 1 over pi n 1 plus this quantity you see, of course, with z not equal to 0. See, so these messes up is not a Hilbert transform. So we get this constant cotangent for this operator, okay? But it is not the discrete Hilbert transform. So this was a really big disappointment to me. However, you know, my co-author, Kwasniewski, is very, very clever, and he did a lot of computations and calculations using numerical calculations. And then it turns out that he discovered or made a conjecture that in fact the discrete Hilbert transform is in fact a convolution of this operator, this probabilistic operator with a probability kernel. Wow, that is beautiful, right? Because then you see immediately, right, by Jensen's inequality, this is a probability kernel, you get that H, the discrete Hilbert transform, is less in norm than this probability operator that we constructed, and we know the probability operator that we constructed has the bound. So there is a proof of the inequality of the Tishmarsh miss, right? And it has been of interest for quite a while. Now, I want to just say a couple of words. So about higher dimensions, right? So of course, we have one example of the singular integral, discrete singular integral that has the same norm as the continuous version. Now the question is, and Calderon-Zygmunt in their famous paper 1952 not only study these operators, but they actually studied the discrete versions, and they proved, just as Ries, that these operator, the continuous ones, have the same discrete, same comparable norm, right, as the discrete ones. And one particular interest that is of current interest, or that has been of interest, is the norms of the discrete Ries transforms, which are just what obtained by taking this kernel and putting in the discrete sequence there, right? And in fact, back to Stein and Wenger and Meiger in 2002 proved this inequality, right? So this is the analog of Ries theorem, and this is the analog of Ries, and after the correction of Tishmarsh. But you see, they show that this inequality holds with a constant that depends on the dimension, independent, so independent of P. And here's what they said: it would be interesting to know the CD can be taken to be independent of D, or for that matter, if C can be equal to 1. Of course, C equal to 1 is the interesting thing. In fact, the Ries transforms in hard dimensions have the same LP norm, as it turns out, not only independent of dimension, but they have the same norm as the continuous Hilbert transform. And so what you want to do in order to solve this problem here for the Ries transforms, forget about general singular integrals of the convolution type, will be to show that the discrete Ries transform, right, the convolution with a discrete kernel, has norm equal to that. Well, we are stuck, unfortunately, and have not been able to prove that. What we can do is construct discrete operators in Rn, which are very much go along the lines of the discrete Hilbert transform, right? But you see, for one dimension, right, in one dimension, we show that the Hilbert transform is equal to the discrete Hilbert transform plus, right, an error term, which is in fact 1 over, which is essentially the convolution of the discrete Hilbert transform with some other kernel, right? And we had very explicit expression for this quantity. It was due to the fact that in higher dimension, in dimension 1, we have an explicit expression for this periodic Hilbert transform, this function, this do function that we use, and we're able to do computations quite easily there. Well, not easily, but eventually we're able to do computations here. We do not know what this. Well, we have an expression for this, but it's really, really very messy, and it doesn't really do the job that we want to do. So we hope that there is an extension and that we can do this other inequality or solve that problem that Stein and his collaborators left, but we have not done that. The most we can do is the one-dimensional case. So let me stop here, and if there are any questions, I'll be delighted to answer questions. Thank you very much for your patience and listening to the talk.
Thank you very much, Professor. Sure, we have time for questions. Is anyone willing to ask something? Please just unmute and you can ask. Well, I actually have a question, Professor.
Yes.
This lemma, you presented this lemma relating the discrete Hilbert transform with this operator tau.
Yes.
It seems very elegant. Is it possible to give some interpretation of this relation?
You know, that is a fantastic question, and I do not know. You see, what is this kernel, right? Well, you know, does it have some probabilistic meaning, right? We do not know. It is if you look at these, right, you see the Hilbert transform here, right? So you see that this is the Hilbert transform. So this is the kernel for the Hilbert transform. And then you have 1 over pi n here when you multiply, right? So this looks like the Hilbert transform plus the Hilbert transform of something else, right? And this is the quantity that we have to study, and there are a lot of computations, some quite a bit of complex analysis. But is there a more, and you mentioned elegant, I mean, I just thought that this was really plain luck, and and of course I attribute this lemma to my co-author, because he was able to sort of conjecture that this was the behavior, but we do not know what is the meaning of this kernel. What does it represent, right? of this probabilistic kernel? Yeah, it's a good question, very good question. Mm-hmm.
We'll see. Maybe someone will search or try to answer that. Yeah,
well, that would be wonderful. Yes. Yeah. And this is the thing that is missing in higher dimensions, right? It would be good if we had a deeper understanding of this kernel rather than just the mathematics involved, right? And the formulation. Then maybe there would be a possibility of making some conjecture in Rn as to what or Rd. I use Rd here because n became the lattice point in the lattice. Maybe some possibility of getting something in higher dimensions, but nothing so far.
Right. So another question is about the Doob H transform. Like usually people associate this procedure with conditioning and a stochastic process.
Yes.
So I didn't quite follow if there is a precise condition.
Well, given any non-negative harmonic function, right? Positive harmonic function, right? Non-negative had to be positive harmonic function. You can construct the Doob H process, right? Namely by this, right? Okay, and the drift of these will depend on the behavior, right? On the behavior of the harmonic function, right? So what this does, right? Under the Doob measure, it makes this process, right, always go to the lattice, right? Because that's where the singularity and actually, that I put a lot of things under not under the rug here, but without explaining, the mathematics that is required to show that these boundary values are in fact that this function u on n comma 0 as y goes to 0 for any n actually give you the function, the boundary values of the function f.
Okay.
Yeah. So
can you put your picture?
Yeah.
Yes, because I noticed something unusual. I noticed like these arrows around these points. Is it something to do with that?
Yeah. This exactly. Well, I mean, this is the only thing I was trying to illustrate with this picture is that this is a Brownian motion up here, right? It starts to run from wherever it started running, okay, y comma 0 up here, right? And he runs, and as he goes to the boundary, it goes to these points. Now, what is the probability? The probability of going to these points. The probability is given by let me see, where is this probability? Right here, Pn x comma y divided by this. You see, h. These numbers add up to h, right? So when you divide by h, these are probabilities. So these are the weighted probabilities for this Doob H process, right? So as time goes on and they are getting close to the boundary, they avoid everything except these points here, right?
Right.
The lattice points. So this is definitely condition, like condition. Yeah, Doob H processes are condition. You can condition them to go, from one point inside a region to another point. You can condition them to go to the boundary, just one point on the boundary. For example, when you take Brownian motion condition to exit at a single point. That's just the Dubage process with respect to the Poisson kernel that has singularity at that point. Right here, we wanted to exit throughout all the points on the lattice. Right? So that is not going to go to minus 1.5. It's not going to go to 0.5. Certainly 0, 1, 2, and so on. I don't know if that. Maybe.
Yes, thank you very much. More questions? More questions or comments? No? Well, then I think we can unmute. Please unmute everyone the microphone, and we can thank Professor Rodrigo Bañuelos. We can give an applause if you want. Thank you very much. Very nice.
Thank you.
Thank you so much.
Thank you, Professor.
So,
Okay.
right. So we have plenty of time for the next